Northwestern. CIERN is our Center for Interdisciplinary Astrophysics. We think about lots of things ranging from cosmology to galaxies to planets to the lives of stars to black holes, all sorts of stuff in astronomy. And the point in what we do is that lots of these things that we think about in the universe are extraordinarily complicated. And so it takes more expertise than one person or one group can offer. And so there's lots of us who have lots of different expertise that work together. I'm classically trained in relativity, in gravity, and I've spent my whole career working in another area of astronomy called gravitational wave astronomy, which we can talk about sometime if you're interested. As we go along, I'll take questions. So if you have them, please just unmute or just kind of interrupt me. That's fine. But I will ask for questions along the way, just in case someone's bashful about interrupting. But invariably, you're going to have some question. 2 weeks from now, you're going to wake up in the middle of the night and wonder something about something I've told you. Most of you know at this point that your spouses don't want to talk about astrophysics at 2 o'clock in the morning. So if you do have a question, my email address is there, s.larson. The dot's kind of hard to see in that star field. Sorry about that. At northwestern.edu. You're certainly welcome to send me email, and I will tell you what I know, point you at things that I know about, books that I've read, whatever that you may find useful or interesting. My blog is there, the rightscience.wordpress.com. That's supposed to be a public level blog. It's about all sorts of things that I think about in astronomy. There's stuff in there about starships, alien life, black holes, gravitational wave astronomy, science in general. It is aimed at the public. As I usually tell people, I write it so my mom knows what I do. So if you're interested, you're certainly welcome to spend some time reading. And then my social media links are there. So as we go through this, I'm going to start with just a little bit of discussion about ordinary travel through the universe to kind of motivate why we're thinking about wormholes. Some of you may know this or know how to generate some of this kind of thinking yourself. So there'll be a few numbers that I've kind of generated and put in place. I'm not going to show you how I got them, but if people are interested, I can certainly give you some information about how to do it on yourself. But I wanted to provide a framework and some information for those of you who are thinking about this. So the beginning of the story about why we're thinking about wormholes is the fact that when we think about our exploration of the universe, no human has ever been any farther from Earth than the moon. And in fact, there are only 24 humans who have even been that far at all. The Apollo astronauts to date are the only ones who have been that far. They are slowly passing away. And until the latest moon program succeeds in returning humans to the moon, they will be the only humans who have ever experienced seeing our planet the way you see it here in this image. Our space probes, of course, have been farther, but they've only been to the outermost parts of the solar system. They've certainly never been to another star. And so trying to understand ways of getting around the universe is intimately tied to this kind of trivia fact that we've never been very far in the universe. And the answer to why that is really what's driving our discussions about how do we travel around and are there exotic ways to travel around as if by wormholes. So the beginning of this is really asking, well, how far away is it to outer space? In reality, outer space isn't far away, right? The boundaries of space are the upper layers of the Earth's atmosphere. Those of you who study aeronautics and space flight know that the altitude at which you can get your astronaut wings is a line above us in the atmosphere called the von Karman line. Roughly speaking, it's the place in the atmosphere where fixed wing flight is no longer possible. So it's about 60 miles over our head. And that point led Fred Hoyle, who's a very famous cosmologist in the 20th century, to note space isn't remote at all. It's only an hour's drive away if your car could go straight upwards. Okay. And that fact, I think, is a good starting point to kind of really think hard about why it's so difficult to travel through the universe. So let's use that as our foundation. This is my favorite car I use when I talk about space travel in classes and public lectures. This is a Yugo. So some of you may know about this. This is an Eastern European car that was popular when small cars were becoming fuel-efficient popularity in the United States in the late 70s. It's famously the central car in the movie Drowning Mona, if any of you have ever seen that movie. So let's imagine driving a Yugo to outer space, and let's imagine some destinations that we could go to, okay? So I've got a range of things there in our solar system, and then out into the galaxy, and indeed to the nearby galaxy, nearest galaxy to us that's similar to the Milky Way, the Andromeda Galaxy. For most of us, the fastest we've ever been traveling is in a passenger jet, which travels at about 600 miles per hour, or in our car every day, which travels about 60 miles per hour. So let's imagine taking a journey to each one of these places, either in a car or in a passenger jet. How long would it take us to get to each of those places? So the first two, these are the places where humans have been. And indeed, in Earth orbit, right, in your car, if you wanted to get to orbit slightly higher than the von Karman line, it would take you a few hours, the kind of time it takes you in an ordinary road trip. A passenger jet, if it could fly straight up, would get there much quicker. That's about 3 times longer than the space shuttle takes. The space shuttle takes between 7 and 8 minutes to get into orbit, but a passenger jet goes a little bit slower, okay? Getting to the moon takes substantively longer periods of time. If you wanted to drive in a car, it would take you almost half a year. Okay, so that's a very, very long road trip. It really is not something most of us do for those periods of time, although maybe some of you trundle around the country, you know, in your RVs in your retirement, rowing from campground to campground, camping and writing and reading in your retirement. But five and a half months is a long time to spend in a car, as you might imagine. 16 days in a passenger jet is actually a little bit more reasonable, right? You can imagine that you may have taken cruises where you've been on ships for that long, and you know, those kinds of journeys are not out of bounds with what we're thinking about. Of course, we don't want to go to the moon that slow, and so the Apollo astronauts, when they made that journey, it only took them about 4 days. Okay, so they go again a little bit faster than a passenger jet would. So these kinds of timescales for the nearby universe, the places where humans have been, are really imaginable as doable, okay? But if we extend out to the rest of the solar system, it becomes a little bit more tenuous in terms of the everyday travel that you and I experience. To get to Mars by passenger car would take longer than the average human lifetime, more than a century. And to get to Mars in a passenger jet would take more than 10.5 years. So you can imagine sticking your kids in a jet, you know, in kindergarten to go on a field trip to Mars. And by the time they got to Mars, they would be in 12th grade. Okay, so it takes a long time at ordinary travel speeds to get to even the nearest planet. And Pluto is even farther away. So Pluto is the outermost boundary of our solar system. We can argue some other day about whether or not Pluto is a planet, but it is really kind of unimaginable how humans using everyday travel could get to Pluto. It is curious to note, though, that at the speeds of a car, it kind of takes 7,000 years or so, which is roughly just a little bit longer than the span of recorded human history. And so you could imagine if our ancient forebears in Mesopotamia or the Middle East had had cars and they had set out for Pluto, they would just be arriving there right now. So the solar system begins to look out of reach. And of course, if you extend that out into the solar system at the ordinary speeds that you and I are used to traveling, there is no way we can even imagine traveling anywhere in the universe. Even in the Milky Way, at the ordinary speeds that you and I travel, the time it would take to get to the center of the galaxy is longer than the age of the known universe. Okay, so this is the problem. The universe is big. And the fact that the universe is of this enormous scale couples with the other two problems that we have when we think about space travel. The first problem is really us. Our lifetimes are short compared to these timescales, and there are other additional problems, namely that we have to be sustained. We need food and water and air and Netflix and all of those sorts of things to keep us occupied on these enormous journeys that we're talking about. The last problem is there's an entire another talk we could do about starships. It's really about propulsion. How do we harness technology to actually get us from one place in the universe to another? And there are certainly challenges on that front, but there's certainly nothing that precludes us from developing awesome propulsion technology and actually being able to travel through the universe if we wanted to. Okay, so the scale is really the big problem, and this is what we're going to focus on today. How do we deal with the fact that the universe is such an enormous scale? The easiest solution would be to just go fast, right? Getting up to fast speeds isn't hard, okay? So really all you do is you get in your car and you hold down that accelerator pedal longer than you normally would. Okay, so this is a little table here. The final speed that you could attain expressed as a fraction of the speed of light is on the left there. Okay, and then I'm going to show you two different columns. One is if you could accelerate the way you can in your car. You just push down the accelerator and that increase in speed you feel, okay, 0 to 60 in 5 seconds, right? If you could sustain that, how long would it take you to get to each of these speeds of light? Okay. The other column, it says 1g, and this is a classic acceleration that you will often see and read about in science fiction, but it's one that we think about a lot when we imagine traveling through the universe, because at those accelerations, the environment that a person on the rocket ship will feel exactly the same as you feel standing here on Earth. If you're standing on the floor of the rocket ship and it's accelerating at 1g, then you just feel like you're walking around your room like you are right now, okay? I will note for those of you who read or are watching The Expanse, the reactionless drive that's used in The Expanse basically corresponds to this 1g column. They think about and they imagine traveling around the solar system using this Epstein drive that they've invented, okay? So what do these speeds look like? So if you could hold down your accelerator in your car for 6.5 days and your car could keep increasing its speed over and over again, then this first column here says that you could get up to 1/100th the speed of light. Okay, that's amazing, right? You and I in our everyday lives never even come close to any noticeable fraction of the speed of light. But if the engineering in your car could let you just hold that accelerator down, it would only take you 6.5 days. If you could do it for 3/4 of a year, you could get all the way up to half the speed of light. Okay, so this first column says, you know, technology that you and I know, accelerations we can easily produce, can in fact get us to fractions of the speed of light if we just sustain the acceleration long enough. Our engines can't do that, of course. Rocket engines might be able to if you could carry enough fuel, but the point is it's not impossible to imagine getting to a substantive fraction of the speed of light. At 1g, which is a much stronger acceleration, you can see the numbers climb up much more rapidly. And so just in a few months, you can get to 1/4 or 1/2 the speed of light, okay? This is why this column here, you see you can get to fractions of the speed of light in just a few weeks. This is why like in The Expanse, they can get around the solar system as quickly as they do, okay? Now, there's a problem here with this, and this is the last table of numbers I'll show you, and then we'll start talking about what we came here to talk about. The problem here, as you travel at ever greater speeds, is that the laws of nature get in the way. Okay, and the specific law of nature that we worry about is called special relativity. So this was Einstein's work on how the universe looks and how the universe behaves when you're traveling at high speeds. There are many effects, many exotic effects that you've probably heard about or read about. For those of you who would like to read more about this, I can certainly recommend some books. But the one that's relevant to those of us who are imagining traveling through the universe is something called time dilation. It says that if you're on a rocket ship that's traveling at a very high fraction of the speed of light, the amount of time that passes on any clock, whether that be a clock on your wristwatch, a biological clock like your heartbeat or your cellular aging, every clock, natural or mechanical, ticks at a slower speed than a clock that's standing still. Okay, so what that means is that if you go fast enough, you can reach anywhere in the universe before you die, but there are consequences for that. Okay, so again, here in the first column is the final speed that we want to attain. And then I'm going to show you how long at these relativistic speeds elapses for you on the starship if you travel to these distant places in the universe. And those of you who read and watch a lot of science fiction know that this is the kind of centerpiece of many works of science fiction. Probably my favorite is that top book there by Joe Haldeman, The Forever War. They actually use a couple of different technologies in that book, but the beginning is this kind of relativistic journey to the collapsar that helps them travel through the universe. Ender's Game famously also uses proper relativistic travel. This is the whole point in the time lag between the books in that series. And those of you who have watched Avatar, they kind of say it in passing, but if you listen and you write the numbers down, you can work out that there's a little bit of relativistic travel going on in Avatar as well. Okay, so let's imagine two destinations. Let's imagine traveling to the nearest star to Earth. So that's Alpha Centauri, 4.3 light years away. And then let's also imagine a journey to the center of the Milky Way, which is 24,000 light years away from Earth. Okay, now these first three rows are very fast speeds. They are substantive fractions of the speed of light, but they actually are a little bit, what do I want to say, not dramatic in terms of the time dilation effect that they have. Okay, so if you and I travel at 0.9 the speed of light, okay, 0.9 c, c is this physics lingo. Whenever we write c, we mean speed of light there. Okay, if we traveled at 0.9 c to Alpha Centauri, aboard the ship, only 2 years would elapse. Whereas on Earth, people not on the rocket ship would experience nearly 4.3 years elapsing. Okay, so that's about a factor of 2 in time when you're traveling at 0.9 the speed of light, but it'll be noticeable, right? Your twin will be older than you, but it's not dramatic. In general, the friends you leave behind won't be dramatically older than you when you get back, okay? Getting to the center of the Milky Way is still impossible, okay? Traveling at 0.9 the speed of light, it will still take 11,000 years for you and I to travel from Earth to the center of the Milky Way. So getting to the nearby universe, this might be great if we could go 0.9 the speed of light. And indeed, many of the kind of most prominent starship designs that imagine traveling to the nearby universe, these are the kinds of speeds that they tend to think about. But to truly travel across the universe, you have to think about these very, very fast speeds at the bottom, okay? So you can't travel faster than the speed of light. You can just get ever closer to the speed of light. 1.0 c is the ultimate speed limit in the universe. And so 0.999, as many nines as you want, is what we're really talking about doing. But look at that bottom row there, right? 0.999999 times the speed of light, okay? 6 nines. If you could travel that fast, it would only take you 2.2 days to get from Earth to Alpha Centauri, okay? That's like the length of time it takes me to drive from Chicago to Tucson, okay? If we could travel this fast, we could get to the nearest star. It would only seem like 2 days to me on my starship, an easy road trip. But for everyone else who left behind, they would have thought I would have been gone for 4.3 years. Similarly, right, the Milky Way is 24,000 light years between us and the center of the galaxy. But traveling at 6 nines times the speed of light, I could get there in 30 years. If I had left for the center of the Milky Way when I started my college career, I'd be there today in terms of my clock instead of talking to you, okay? But for everyone left behind on Earth, they would think there'd still be 24,000 years before I'd finally get there, okay? So this is the penalty of relativity, okay? At high speeds, if I want to go to Alpha Centauri or the center of the galaxy, I can get there. But the length of time for people who remain behind on Earth is enormous. Okay, you can go visit any place in the universe you want to, but you're never going to be able to come home and tell your friends about it. Okay. Carl Sagan has a great bit about this in episode 8 or chapter 8 of Cosmos. If you're reading it, he talks about this kind of journey, this circumvention of circumnavigation of the universe at high speeds. Okay.
Question?
Yes.
Question?
Yes, Tim.
Yeah. In the last at 0.9999 whatever, and we go 2.2 days. Does it means that the astronaut or the cosmonaut will have to have 2 breakfasts, 2 lunches, and 2 dinners? Is that how it is?
Yes. Yes, that 2.2 days is the time that you think passes on the ship. Okay, and when we say time that passes, it's everything that you might use to tell how much time has elapsed. So your biological system and your need to eat on a regular schedule, that's exactly what it means.
Thank you.
Okay. Other questions? Okay. So what's a poor cosmic traveler to do? Okay. This is traveling this way, traveling the way we think about traveling is hard. And there are consequences for it, right? It's, you know, it's great for you as a traveler. You can go be a tourist, but you won't get to come home and show everyone all the cool things you saw out in the universe on your trip, okay? So people have been thinking for a long time about ways that you could circumvent this. And there are exotic ways that are probably not within the boundaries of the laws of physics. There are things that people make up, but the ideas have seeded new ideas in our thinking about the way nature works and what might be possible. And so I want to talk about some of those, okay? And all of these are basically rooted, right? The idea that the ideas I'm going to describe to you, we are assuming that the universe works the way we currently understand it works. We are assuming that the universe's fabric, the substance that it is made of, is what we call space-time. It's the stuff that is described by the modern prescription for gravity that we use to understand the universe, which we call general relativity. Okay, so in order to talk about that, let's begin by considering travel on a 2D surface. Okay, so this is completely analogous to what you will hear us relativists say. We talk about traveling in flat space or traveling in Minkowski space. This is the place where I'd like to start. Okay, so we often describe Minkowski space or flat space as a piece of paper. Okay, so this is completely the reason we call this flat space. The piece of paper is flat in every sense. It doesn't have to be laid on your desk. You could wrap it into a cylinder that gives it different properties. But the point is the surface is a 2-dimensional surface that can be tiled, as I've done it here, with a perfect grid. Okay. Now imagine on this space-time, we have some cosmic travelers, in this case, in the form of ants. And these ants would like to travel from one place, wherever they happen to be in the space-time, to somewhere else. Okay, and most ants want to get there as quickly as they can. And so they travel in a straight line and they can move without penalty from one place in the universe to another. You don't have to travel the way those ants did. You can take a more circuitous path, but it won't be the quickest path. Okay, you can still travel everywhere in the universe you want to, but you go at a different pace. Okay, and this is really the lesson about traveling in the universe, is the time it takes you to get from one place to another depends on the path you take. Okay, and all of us learned early on in school that the shortest distance, which usually we mean actually putting a ruler down on a page, but in the context of travel, we often mean time. Okay, the shortest distance between 2 points in flat space. Okay, we never say that when we teach you this in 3rd grade. The shortest distance between 2 points in flat space is a straight line. Okay, But let's imagine we aren't in flat space, or let's imagine we didn't know we were in flat space, and we were just watching ants walking around on space-time. If I just have one ant I'm watching, I can't really tell anything about the space-time at all. Maybe that ant is, just wandering around like our red ant in the last picture. And so this path that this ant is taking is just part of its circuitous wanderings, its exploration, its tourism of the universe in which it lives. Okay, but if I watch many ants and I kind of keep track of the paths they travel on, and I watch them over and over again for long periods of time, I will begin to notice patterns. Okay, and those patterns, when correlated with each other, do not necessarily correspond to ants constantly wandering around. They will point to the idea, the notion, that the space upon which they are wandering is not flat at all. It's not what you and I have been calling Minkowski space. It is, in fact, some other curved space-time. And if there are enough paths, you can discern what the shape or boundaries of that space-time will be. In this case, it happens to be a champagne bottle that our little ants are walking across. Okay, so the lesson here, which we wholeheartedly embrace in relativity, is that the shape of a surface means there may be interesting pathways that lead from one place in the universe to another. There is always a shortest path. The functional equivalent of the shortest distance between straight lines is shortest distance between 2 points is a straight line. Okay, those of you who like fancy words in relativity, we call those geodesics. Okay, that is the shortest path between any 2 points in a space is called a geodesic. That always exists, even on this champagne bottle, but you're not required to follow them, and there may be other interesting pathways you could follow. Okay, so. Well, actually, let me ask, is everyone okay with that? Are there any questions before I use this to make something exotic? Okay, rock and roll. Okay, so one of the things that we know about nature, one of the things that we've learned about nature from general relativity is that nature knows how to bend space-time. It does it with mass. And this is a very classic picture that you see when you learn about general relativity. If you spend some time on my blog, you'll see some writing about this that kind of walks you through this idea from beginning to end. You will see that space-time is often described as this kind of large elastic membrane, and that membrane can be bent by the presence of large masses. In this case, in the center, there's, say, the Earth or the sun, and orbiting around it, you'll notice there's a little dimple next to it where it also is distorting the space and time, is a smaller body. If this is the sun, this is like the Earth. If this is the Earth, this is like the moon, okay, and it orbits around. You will hear us constantly use this language in science fiction a lot, but in physics as well, where we talk about the gravitational well. Okay, this is the origin of that. The space-time is bent into this depression, or indeed it can be very deep and very steep hole, okay, where the space-time has been bent into a shape that in our everyday human experience looks like a well or a bowl. It could capture water if you could somehow pour water into that surface. So this is where that language comes from, okay? So if nature knows how to bend space and time, it can make these gravitational wells. We see them all the time. We can measure them. We travel through them all the time with our spaceships. If nature can bend space and time, then perhaps the possibility exists that it can bend space and time in very exotic ways that could make shorter pathways between one place in the universe and another. Okay? And so this is the kind of classic picture of this. This is what we call a traversable wormhole. This grid represents, that's bent into a U shape here, is the space that you and I walk through every single day. It's basically like the grid that our ants were walking around in on the first slide that we showed. And if the ants wanted to go from this place in the universe to this place in the universe, normally they would walk along this straight line that goes along the grid from one side to the other. But the fact that nature can bend space and time into any shape, okay, suggests maybe there is an exotic shape, which you see here, a wormhole, a tunnel that goes from one place in the space to some other place in the space. And so if our ants walk this way, it may take them a long time, 10 years or 10 miles, to go from one place in the universe to another. But if you follow this pathway down this throat, as we call it, down this hole, you would emerge in the same place after traversing a much shorter distance, possibly for a much shorter period of time. Okay, so this was the fundamental idea, and people imagined that this might be possible a long time ago. The name wormhole comes from imagining this on an apple. An ant wants to walk around from one side of the apple to the other, but they could get there much quickly if a worm had bored a hole through the center of the apple. And that's where this kind of language comes from. Okay, so this was an idea, but that doesn't mean, just because we have an idea, doesn't mean it's possible within the laws of physics. Okay, but as it turns out, this may be possible. And the reason we know that is because when Carl Sagan was working on his novel Contact, he very much wanted to not violate the laws of physics. Okay, so hopefully some of you have read Contact. Many of you may have also seen a very excellent movie made based on the book. So Sagan wanted to not violate any known laws of physics. And so he went to Kip Thorne. So Kip's a professor at Caltech. I was actually a postdoc in Kip's group when I was right after I got my PhD. Sagan asked Kip whether or not there was some way to make this kind of instantaneous travel from one place in the universe to another possible. Okay, and we all kind of knew about this kind of wormhole idea. So Kip sat down with one of his students, Michael Morris, and they worked out a way that this could work. Okay, and so there's a very famous paper that's been published by Kip and Michael in the American Journal of Physics. There's a citation down there at the bottom. Those of you with university connections can probably find that. You can find it in print in libraries, but if someone really wants this paper, it's got a lot of math in it, but if you really want it, I can certainly get a PDF of it for you to look at. So this is the wormhole paper. This is the paper that basically said this should be possible within the confines of general relativity. So we usually in physics call these things Morris and Thorne wormholes. And this is the abstract of the paper. And I put it here not because I need you to read this or want you to have all these numbers, but they make two statements right here in the abstract that I think are relevant to our thinking about wormholes, particularly in the context of science fiction and whether or not it's really possible within the laws of physics. The first here, he acknowledges that they're doing this in connection with Carl's novel. But the last part of that sentence there, I think, is the most important one. And I think it very much reflects the ethos that we have as scientists, which is according to our current best knowledge, as Kip says there, the best 1986 knowledge of the laws of physics, this should be possible. Okay. We understand nature in a certain way, and as far as we can tell right now, nature does not preclude the existence of these kinds of wormholes. That doesn't mean our understanding of nature isn't changing, and that when we understand the laws of nature better, we may decide that these things are not possible. And indeed, many of our colleagues have examined reasons why this may or may not be possible, or ways it may or may not be difficult to create such wormholes. But as of the moment, there's nothing that precludes their existence. Okay, the big obstacle is right here in the very last sentence. Okay, we'll talk about this again in a moment with regard to warp drives, but in order to make wormholes, you need to have something that we generically call exotic matter. Okay, exotic matter is something that we have never seen in nature. It has certain kinds of properties, but there's nothing that we know of that would, again, prevent us from discovering it, or that would preclude its existence in nature. Okay, and as Kip says there, right, this is the existence of this stuff would violate some of these kind of deeply cherished ideas that we have, but quantum theory, right, gives these kind of tantalizing hints that this exotic matter may in fact exist or be possible to create. Okay, and so that's the thing that most of us kind of still sit on and recognize may be the kind of key point in this whole affair. Okay, so these wormholes, of course, they are popular in science fiction. I think most of you know many examples. The kind of most well-known and widely known example is the Bajoran wormhole in Deep Space Nine, for those of you who are trekkers out there. The opening of Interstellar, there is a wormhole near the orbit of Saturn, which they use to travel to Gargantua, the distant black hole in that movie. This is my omnibus edition of one of my favorite pair of novels by Greg Bear, Eon and Eternity, which wormhole features very prominently in. And those of you, again, who are fans of The Expanse, if you read or watch The Expanse, the device the protomolecule builds is in fact gateways that open up wormholes. Okay, so wormholes are kind of standard ideas in science fiction these days, but the great thing about, compared to the time I started reading science fiction and my life now as a professional physicist, is that in my discipline we've kind of finally given these things a little bit of let's call it an existence theorem, a proof that indeed this may be possible. Okay, are there any questions about this? And I'm going to talk about warp drives. Okay, rock and roll. So warp drives, like wormholes, are a kind of a standard, I suppose, in much science fiction. The classic name warp drive, I think, probably comes from Star Trek. That's certainly where I associated with. And so our demonstration image here has the venerable Enterprise D here immersed in its warp bubble. Okay, now for a long time, there was no real solid thinking about how this was possible. Okay, the idea of warp drives and how to do it was a bunch of technology, as we call it, a bunch of technobabble, just kind of saying, oh, maybe we could do this and maybe it would work. Okay, but once the Morse and Thorne wormholes were kind of established, it kind of pushed our thinking a little bit and kind of encouraged us to kind of be more diverse and broad in our thinking about what might be possible in the context of manipulating space-time for the purposes of travel. Okay, and so one of our colleagues who he was at Cardiff in the UK when he wrote this paper, Miguel Alcubierre, he's now a professor at UNAM in Mexico City. He wrote this very famous paper, and so the warp drive I'm about to describe to you is usually called the Alcubierre warp drive, and many of us have written papers on it. I've written several papers about this, but this is kind of the fundamental basis for the idea of having propulsion by bending space-time as opposed to finding weird paths through space-time. Okay, and so it's kind of illustrated in this image here. Okay, the key point to note, to remember about the Alcubierre space-time is to look at the space right around the Enterprise here. Okay, what you see is the grid is that perfect grid that we had when we first drew our space-time for the ants several slides ago. Okay, the space that you live in, the space that you experience when you're on board the ship in the warp bubble is flat, which means there are no deleterious relativistic effects that you experience. In particular, the whole point in the Alcubierre warp drive space-time is to prevent time dilation from taking hold on passengers in the starship. Okay, but what the warp drive does is it compresses space-time in front of the spaceship, and it expands space-time behind the spaceship. So this bubble is caught between a collapsing bit of the universe and an expanding bit of the universe, artificially created by the warp drive. And the net result is a propulsion that drives the ship forward. Basically, the warp bubble the ship is contained on is surfing on this moving distortion in space and time. And that's the fundamental principle behind the Alcubierre warp drive. Okay. Now, I said this was motivated, or at least inspired, or kind of made us realize this was possible from the Morris and Thorne wormhole work. And the connection between those two is that in order to make this happen, in order to be able to build a warp bubble where space-time is compressed in front of it and expanding behind it, you have to be able to manipulate space-time. And in order to do that, once again, you need some of this exotic matter. And the key to the Alcubierre warp drive is being able to control where the exotic matter is so that it produces the distortions that are expected or needed in order to make this kind of propulsive effect, this surfing on space and time. Okay. And so this is, right, this is not precluded by the laws of nature, but there are two huge obstacles. One is we have to find some of the exotic matter or be able to make it. And then two is we have to be able to manipulate it and control it and shape it in such a way that we can make the warp bubble that we need. Okay. But again, right, our ethos as scientists is that's an engineering problem. The laws of nature as we understand them right now don't prevent this from happening. So yes, we could have a warp drive, right? So that's kind of cool. Okay, any questions about this? And I'm going to tell you one last thing about higher dimensions, and we'll call it a day. Okay, rock and roll.
I have a question.
Yes.
You mentioned that there would be a, if I understand it, an innate propulsion, just because there is this difference between the front and the back of that spaceship.
Yeah, so the expansion behind you kind of pushes the bubble forward, and the compression in front of you kind of draws you forward, like you're falling down a well. So
Okay.
This is what kind of gives that propulsive effect, this feeling that you're surfing on space-time.
But okay, and
so it's I mean, I think that analogy with the surf wave is exactly right. When you're on your board, the rising water behind you is pushing you forward, and the descending water in front of you, you're running towards. That's really what's going on here.
Okay, I understood that. And then, but the universe is much more complex, and it has many other planes and many other, in other words, what I'm looking at, this is still a flat dimension, you know, but aren't there more others intersecting planes with different wells and different thing? Yeah, how you know, theoretically I understand it, but it gets more complex in real universe life, isn't it?
Yeah, so that's a great question. So I'm going to talk here next about dimensions other than the ones that you and I live in. So that may in fact be a complexity that's related to this that will have to be worked out. So let me kind of table that for a moment.
All right.
The thing that's important about the universe on large scales is that if you look at the universe, it does have a shape, it is curved, but there is this fundamental principle that the space near you is, as we say, locally flat. It means it's very hard to detect that the universe is slowly stretching, that it may have some shape to it in the area that's very close around you. And the kind of classic analogy that we encourage people to do to kind of give them a sense of this is, you know, if you look at a basketball is very definitely round, but if you put your eye very close to the surface, the space right in front of your eye, when you're confined to that very small piece of the basketball, looks nearly flat. And that's kind of this same idea in the universe, right? Is that on the largest scales, it is complex and it does have shape, but on the scale of a spaceship, it's more or less equivalent to flat space. And the idea that I'm describing here should work. Okay.
Thank you.
If you travel near a star or a black hole or a planet or something where the space is more strongly shaped, then absolutely there could be difficulties. But, you know, that's for your navigators to deal with, I think. So, okay.
Excellent. Thank you. Yeah.
Other questions? Okay. So this was alluded to. Let's talk about higher dimensions. So this again is the same kind of grid shape that I showed you a couple slides ago, where we had the wormhole connecting two distant places in the universe. But imagine that the wormhole didn't exist. Okay, so if you're a poor ant and you want to travel from the star at the top here to the star at the bottom, you are completely confined to traveling along the space-time grid. Okay, and the space-time grid that I've drawn here represents the space that you and I are used to living in. Okay, so this is 3 dimensions of space, 1 dimension of time. We're representing that here as a 2-dimensional grid, and time is however long it takes you to walk along the green arrow. Okay, but it has always been supposed that maybe there are higher dimensions in the universe. Okay, and this was alluded to a moment ago in Tim's question. Okay, so imagine that you were looking at this universe the way you and I are here. You and I aren't living on the grid. We're standing outside the grid, just kind of looking at it. And so there is some additional dimension. This grid is 2-dimensional, but to draw the picture that I'm showing you, there's actually 3 dimensions. So if you're a person living in Flatland, the classic book from the 1800s, right? Space is 2-dimensional, but if you can look at it from the outside, maybe there's a higher dimension, a 3rd dimension in this picture. And so if that's possible, then it has often been supposed or speculated that why do I even travel through the dimensions that I exist in at all? Okay, maybe it's possible to take a shortcut, to jump through the bulk, as we say, or through those higher dimensions, step off of the dimensions in which I live, and walk across the dimensions, and then come back to the lower dimension where you and I exist. Okay, so this is, so Sagan again in Cosmos, he does this famous demonstration, the Flatland demonstration, where a Flatlander is lifted up above Flatland by an apple in 3 dimensions and then returns to Flatland. Okay, so this is basically that premise. Okay, so if you could travel through those upper dimensions, then maybe you could go from one place in our universe to another without penalty. Now, it's not clear you can do that. It's not clear that the laws of physics, as you and I understand them, apply in those higher dimensions. Maybe the laws of physics are different, or there are other laws of dimensions in those higher dimensions. But nonetheless, if they exist, then the supposition, the question is whether or not this is possible. Okay, now this smacks vaguely of what we typically call hyperspace in science fiction, but I think that's the kind of right idea to have in your head. I was famously exposed to this idea at a very young age, and I'm sure many of you were as well, when I read A Wrinkle in Time. I remembered that, so this is from my collected omnibus of the quartet. But there's this picture that, you know, when I was in 2nd grade or whenever I read this, it stuck in my head forever of Mrs. Whatsit and Mrs. Who explaining to Meg Murray how this kind of interdimensional travel works by imagining an ant walking along a string, and if they could somehow jump through some other dimension, they could bypass traveling along the whole string. Okay, so that's I think the right picture to have in your head of this whole notion. Okay, now the last thing I want to talk about is black holes. Okay, so black holes are famous targets for all of this business because it has long been supposed that, in fact, black holes may harbor tunnels to other places. And I put a little asterisk right there because this idea that black holes may have tunnels is in the same vein that you and I have been talking about, is really a mathematical one. Okay, and I have some pictures in the extra slides if people want to see them to kind of show how it works. But the mathematical description of black holes says that if you go inside, there may be possibilities that there are tunnels that you could travel through without penalty. Okay, and that is an untestable fact. okay? Because the whole point in black holes is that if you travel beyond the surface of the black hole, the event horizon, as we call it, there's no way for you to communicate anything about what you discover inside the black hole to the outside world. That's what the event horizon says, right? The event horizon is an impermeable membrane that prevents information about, whoa, folks, there's a tunnel in here, from coming back out to everyone on the outside. Okay, so that's what that asterisk really is about, is that right now we don't know of any way to communicate whether or not this is true by any experiment we could do about what the interior of a black hole might look like. Many of our colleagues think that nature likes to close off the tunnels. We've done studies that suggest that may be true, but again, right, our understanding of the way gravity works on the smallest scales is not well formed. And so it may or may not be true that nature closes off these tunnels. But for you, I will note there's basically three kinds of black holes, okay? The kind of classical black hole that you hear about is a perfectly spherical black hole, what we call a Schwarzschild black hole, okay? Many of you will have heard the term Einstein-Rosen bridge, okay? So that comes from Schwarzschild or spherical black holes. And the Einstein-Rosen bridge, despite the fact that it's often used synonymously with the term wormhole, is not actually traversable. Okay, so inside perfectly spherical black holes, there are not tunnels. The Einstein-Rosen bridge exists, but you can't get on it and travel across it unless you can exceed the speed of light. And in our conversation here today, we're trying not to violate the laws of physics. So the Einstein-Rosen bridge is not traversable in that instance. But if you could somehow take a Schwarzschild black hole and put some electric charge on it, right? So give the black hole a fork and ask it to stick it in an electrical socket, right? All of the electrons, the electricity, if you could put it on the black hole, then in fact, there would be a tunnel through that black hole according to general relativity. Okay, so these are called Reisner-Nordstrom black holes. Okay, so these tunnels exist. I put a star there next to the yes because astrophysically, we don't expect black holes to be able to sustain electrical charges on them. Okay, those of you who remember your basic physics, they remember that opposite charges attract. And so if I were to put a whole bunch of electrical charge, say electrons, on a Reisner-Nordstrom black hole, they would naturally attract positive charges from elsewhere in the universe. They would neutralize each other, and the Reisner-Nordstrom black hole would indeed become a Schwarzschild black hole. Okay, but if you could somehow sustain the charge on Reisner-Nordstrom, then these tunnels should exist as relativity predicts. The most common black holes in the universe are spinning black holes, okay? And we, in fact, expect all black holes to be spinning black holes because it's very hard to keep things in the universe from spinning. And these are called Kerr black holes. And there is very definitely a mathematical description of a tunnel that exists inside a Kerr black hole. Okay, there are in fact two different tunnels inside a Kerr black hole. One leads to somewhere else, and there is an exotic place inside the black hole through the middle of what's called the ring singularity that usually goes by the name antiverse. And the antiverse inside a Kerr black hole is a weird place, and there's kind of exotic things that may or may not happen there. Okay. So tunnels in black holes, of course, are not new to science fiction. At a very young age, again, I was exposed to this idea in the black hole. Lots of people put a lot of hate on this movie, but you know, in as much as ancient movies often do things wrong and have kind of weird ideas about cultural things, the physics in this movie is not the right physics that we use in general relativity. But what I like about movies like this is that it has enough of the right ideas that it gives you an opportunity to talk about what physics really says about exotic objects like black holes. And indeed, inside the black hole in this movie, there is a tunnel to Otherwhere. And so that's one of the reasons I like this movie. Those of you who have seen Interstellar, we mentioned Interstellar earlier. There's a wormhole at the opening of Interstellar, but at the ending of Interstellar, they travel through the black hole as well. So, Okay, so that's all I'm going to say. There are many possibilities that may allow unconditional or unrestrained travel through the universe that have to do with the ability of us as technological beings or the universe itself to bend space and time in exotic ways. Okay, and our understanding of laws of nature, the caveat I've given you along the way, is incomplete. So we don't know if there are going to be impediments to the kinds of manipulations I've told you about, or phenomena that will prohibit these kinds of strange space-time structures from forming. But at the level that we understand nature today, all of these things should be possible, and in fact, may be realizable. And as scientists and astronomers in particular, we are constantly on the lookout for strange phenomena that may or may not be the signatures of these kinds of exotic phenomena out there in the universe. So I never like to leave you without more to read. So I'll point you to these 3 books. 2 of them are by Kip. This one at the top is probably the best one that's a reference for all of this space-timey stuff. Kip wrote this in the 1990s after he had written the wormhole paper with Michael Morris. Black Holes and Time Warps, this won a Public Science Writing Award. It really is a fantastic book, and I highly recommend it for those of you who like thinking about this sort of stuff. He wrote a companion volume to Interstellar. So there's an entire chapter in the Science of Interstellar about the black hole. There's an entire chapter about wormholes. There's all the science in Interstellar Kip talks about in there. And one of the things that I really like about this book is that Kip gives his own personal rating of all the science that's addressed in the movie about whether or not it's possible, kind of maybe, or whether or not it's highly unlikely. And so I think if you're trying to kind of stay accurate to kind of what we understand and believe is possible in the laws of physics, this is great because Kip kind of gives his personal reference there as to what he thinks the likelihood of all these exotic things are. And then for those of you who think about starship travel, which is kind of what we were alluding to at the beginning of the talk, this book by Malov and Matloff is absolutely my favorite. I have 2 copies of it, so I have one both in my office at work and my study here at home. What I really like about this book is it's kind of 20-ish years old now, I think, but it consolidates in one place all of the kind of classic real ideas about real starships in one place. So there's kind of a chapter about each starship design that people hear about: ramjets, star wisps, Daedalus, Orion, all of them. It has a whole bunch of prose, so you can certainly read it if you're not a mathematically inclined person. But then for those of you who like to tinker with the mathematics, then it's kind of set aside lots of the calculations into boxes. And so you can kind of use this book either way that you think is useful and interesting for your own work. Okay, so that's a few things to get you started. I am going to say thank you so much for your attention, and I will end there, and I'm happy to chat for as long as folks want to chat.
Good. Thank you.
I'd like to thank our speaker. This was a fantastic talk, I think. Very well prepared with lots of references and things to go ahead on. Also, the invitation from Shane that anyone who has an idea, especially those that are trying to write short stories or anything, but even if you just have a question, to contact him directly. A lot of people have a misimpression of scientists that they're very remote and you cannot deal with them. They're off in the ivory tower. But everyone we've had, but especially Shane, but they all, say, well, write to me. I mean, I'm talking about robots or whatever. And if you want to write a plot, just run it by me. So we thank you very much. There has been a shift in time. And because we're international, Ian managed to get here, but Dr. Coster Malaya, coming from Zambia, was not able to understand or to get the shift. And it was, it's our fault. We're kind of weird in Arizona. So he came in a bit late, and so we did not get introduced to Dr. Malaya, but sometimes he has some difficulties talking. He might be able to talk in chat and introduce himself. So I will await word from Dr. Malaya for a minute here. Are you there, Dr. Malaya? Well, perhaps he'll be writing us in chat. And the other person who came in a bit late was Gary Meckler. And he's also in the field of astronomy here in Tucson. So perhaps Gary has a question and could do a brief introduction. Are you there, Gary? Well, we'll leave it open for the two of them. If
Okay.
either one wants to say something later. I just wanted to include them since they missed out on being in the introductions. So any other questions? Gary, is that you?
Oh, can you hear me? Hi, Bruce.
Yes.
I see Bruce here.
No, I hear you.
Oh,
Go ahead, Gary.
well, I didn't really have a question. I had some questions, but I found myself getting answered in the next minute or so when I thought the question up. So, no, you're right. This was, Dr. Larson, this was very, very good. Nice talk. You've done it before, I think.
Actually, this is a brand new talk, so I'm really appreciative of the invitation.
Wow.
I get asked about this all the time, so it's great to finally write a talk and be able to have it there for people to ask about and talk about. So thank you all for asking about it.
Yeah, well,
Oh
thanks
yeah,
for
this was
Okay,
being here.
I have a question.
Oh, could you raise hands from now on if we're because it's getting a bit
Raising
crowded.
hands, okay.
Yeah, but sure, Karen, go ahead.
Go ahead, Karen.
Okay, hi. The question that I had, so when you talk about exotic material,
Mhm.
right? Is that in the same realm as dark energy, dark matter, meaning it's just a term because we don't know what it is? And the only difference here is that maybe it's something that we can create.
Yeah,
The other, dark matter, dark energy, I assume
yeah.
maybe we can create them someday, but we're not thinking about creating that today.
No, that's a great question, and that's a great observation, right? The whole point on dark matter and dark energy, the reason they have such obtuse names is we don't really have any idea what they are, right? We know a little bit about the influence they have on the universe, and we know how to look for them and kind of convince ourselves that they're there, but we've never created some in the laboratory, caught some in the laboratory, been able to do experiments on it. So we don't know what their properties are other than what we see into the universe. And in many ways, the properties of exotic matter are exotic in the same ways that, say, dark energy is exotic, right? It has kind of weird gravitational effects, and it violates some of these kind of classic ideas that we value in relativity. The difference between exotic matter and something like dark energy is that dark energy is really, you should think of it like a cosmological fluid. It fills the entire universe, and it exists on every scale from you and I here on Earth to the farthest reaches of the universe. So it's a cosmological substance. And when we talk about exotic matter here in this case, we don't know what we're talking about. Maybe it is dark matter or dark energy or something like it. But we're really talking about a substance that could be concentrated and gathered and contained somehow, stuck in a water bottle and carried on your starship if you want to. That's the kind of primary difference. It's not this kind of effervescent fog that permeates the entire universe. It's something that you could contain somehow and carry around. Does that help?
Thank you. That's great.
Okay. Other questions? Ian's raising his hand.
Thanks. Can you hear me?
Yes.
Okay. We're mostly odd science fiction writers. It means that we try to incorporate as much real science into our books as we can, so that the student or the reader can learn real science from it. What I see as being an optimal strategy here is to have one lie only, one breaking of physics laws, or one breaking of what we know today as being the truth. What one thing would you suggest is the best item that you've mentioned today to break away from, and in order to ensure that we can tell our readers afterwards, the only thing we lied about was the anti-gravity shields, or the only thing we lied about was etc.
Yeah, so I think the answer to that question depends on your personal belief on what breaking means, right? So let's go back to what Karen was just asking about the exotic matter, right? We don't know that the exotic matter exists. The laws of nature as we understand them don't preclude it existing, and the kind of tantalizing evidence from laws of nature we don't fully understand suggests it may exist. And so the personal question for you is, if I want to use exotic matter to open up wormholes or have warp drives, am I really violating the laws of physics or not? I'm making an assumption that's beyond our current understanding, but there's nothing right at the moment that precludes it, right? So there's that kind of nuanced bit that you have to kind of come to grips with. I think, like going back to the black holes, right? The black hole that I could put electric charge on would have tunnels through it, these Reisner Nordstroms. But there's no kind of such realistic way to protect it from accreting charges from in outer space and discharging itself. But if you wanted to invent some exotic technology that you could protect the black hole, then you could imagine that happening. Put it inside a Dyson sphere or whatever you want to do, right? So there are I would say bendings of the rules that I'm completely comfortable with, but none of this that I've described to you breaks the rules as you and I currently understand them, right?
Okay, thank you.
Okay. Gloria, you're physically and virtually raising your hand.
We come from the last two meetings, which were very ethics and legalities of, and you may want to see these, Shane, about
the YouTube channel, yeah. So
the legal ramifications of robot personhood and how robots should be used. And it was, the technologies were touched upon, but it was more into the realm of human interface with this. Mm-hmm. And I'm thinking, because of Elon Musk and the very wealthy, we went to the Worldcon in Chicago, Shane. I don't know if I told you about that, in September. And one of the guests was Stephen Barnes, who wrote a book called Saturn's Race with Larry Niven. Have you read that book?
That's a great book.
That certainly goes into the class structure of this society. Who gets to go to space? Is it only Elon Musk and his descendants? If so, why should we care? Or are there other technologies that may include more of humanity, but what will be the hierarchical structure? It used to be, when it was government, there was a default we and you, and we always assumed everybody. But now it's becoming clear that a great adventure for some, maybe a very few some of us and their descendants. And it's a whole different talk. But if you think about that, maybe we could do more of a human interface talk. Would you be willing to cover some of that? Because that is kind of
lots of interface there that's important. So when I do my Starship talk, we actually talk a little bit about some of this, because if you assume that our technology isn't going to get better quickly, right? The kind of only default Starship technology that really is imaginable is generational starships, right? And so there, how does human culture persist? How does government sustain itself, whatever, generational starship? And what are the ethics of your descendants, basically taking on your mission because you sent them on this, 50,000 year journey across the galaxy. So we talk about that there. I think there's interesting questions that interface with all of this, particularly in discovering the laws of the universe that we're grappling with right now because of the advent of AI. One of the things that's happening is we are taking very complex data and teaching machines how to look at it. And the machines are discovering, nuances in the data, which could have tremendous impact on the sorts of stuff you and I are talking about, the nature of dark energy, our ability to manipulate space and time, whatever. But we don't really understand how the machines figured out what they figured out. And that's kind of giving lots of people the willies, because, we kind of have this notion that we should know what the machine thought and why. And I often point out to people, yeah, but it didn't bother you when Einstein figured it out and you didn't know what he was thinking, right? So why are you bothered that the machine's thinking this? But there's rich conversations to have there.
Well, I thought more about the inequalities in society. That's what
Oh, yeah.
you know, what they were writing about in Saturn's race was who got to go. It
Yeah.
isn't everybody. When I mentioned once Elon Musk, we used to have a government program, so everybody felt part of the us.
Yeah.
Now we're getting, you know, the privatized, me and my kids are going by, you know,
Yeah.
so I want to really emphasize that. How are you going to keep the poor, especially, caring or not even resentful of this when it appears more and more that it will be Trump's kids, you know, that go,
That's
or
right.
somebody's
The
kids,
space
not us.
tourists are all millionaires, right? Yeah.
So that was what I meant. And we got into that a bit with robots because that has a definite aspect of automation and the future of employment and what kind of society, what will you do with all these redundant people?
Yeah.
So that's also a big aspect today of science fiction, not just how we do it, the processes that we can do it, but who is going to benefit, what's the cost and benefit for the different segments of society. I felt obligated to bring that up because often when we're into the very physics and astronomy, especially parts, it can get lost in the processes that are involved. That would be a whole different presentation. And we would love to have you, you know, maybe talk to some of the books you read, like Saturn's Race by Stephen Barnes and Larry Niven that get into it. And I know there are many others
There are
because,
plenty. Yeah,
you
that's
know,
right.
colonization is not for everybody in a lot of these books. So any other questions?
Tim's got his physical hand up there.
Okay.
Yes. Well, what a privilege to attend your talk and be able to interact with you. It was really quite fantastic. I have a couple of questions, if I may. One is, you mentioned the spinning black hole as the most probably realistic theory or possibilities. And they do, through your calculations, that they do have tunnels. Are these tunnels prefixed? They are from one side, one point to the others, and you cannot manipulate. So if you go into one tunnel, you really don't know where you're going at the other end. And then I'll wait for the answer.
Yeah. So I think the answer is yes, right? When we mathematically describe the interior of the black hole, the full mathematical extension leads through the black hole, and on the other end, there's what many of you have heard the term a white hole. Okay, and if you emerge from the white hole, the open question, you emerge into a normal area of space, just like you and I. Mathematically, it looks the same. And the question we ask is the other space them? Is it some other universe? Or is it somewhere else in our universe, right? And that's the open question. We don't know. And in fact, there are a multitude of paths through the black hole into spaces. And so there may be many kind of ever forking tunnels, off ramps through the black hole that emerge into other spaces that may or may not be in our universe. I think as astronomers, what we do, or what we don't, there aren't any active searches that I know of, but what we would notice is if a white hole opened up in our universe, it would have a very distinct signature and we would see it in our observational data. So, you know, the universe is a big place. There aren't that many telescopes looking at the sky. So it's perhaps not surprising that we haven't seen a white hole. But, you know, that doesn't mean they aren't out there. And many of you may know we are currently embarking on a new era of astronomy where we are going to be generating. So the Vera Rubin Observatory is about to come online. It will generate 20 terabytes of imaging data of the sky a night, and for 10 years it will look at every point on the sky every 3 days in 5 different colors. And so there will be 10 million events, flashes of light, something happening that didn't happen last night, every single night. in the LSST data. And so it's entirely possible that in the next 10 or 20 years, me and you and undergraduates sifting through this data may find something exotic where the only explanation might be, well, maybe that's a white hole. We don't know. Okay, but right, the burden of proof is on us, right? We can't just say, oh, that's a white hole. You know, it could be a variable star, it could be a cataclysmic variable, it could be a supernova, right? There's all kinds of things that it's likely going to be. But as astronomers, we can't exclude that possibility. So
the second question, thank you for your explanation. The second question is about CIERN, the Large Hadron Collider.
Yep.
And when it started to you know, in the days before it started to operation, there were a lot of astrophysicists, maybe few, that warned us that this could be a dangerous experiment. It may open portals like wormholes or something, and or may produce tiny black holes, theoretically speaking. What's your thoughts on that?
yeah, so let's talk about the space-time ripping bit, right? So one of the goals of CIERN is to collide the particles together at high enough speeds and high enough energies that every particle, protons, whatever it is they're colliding together, disintegrates into the constituents that create them. So basically quarks and gluons. Okay, so they're trying to create the so-called quark-gluon plasma, which is what the universe was filled with in the earliest moments of the universe. Now, in as much as it takes a lot of energy to do that, you're only going to get back to that kind of energy scale that the universe is used to have being made when all the particles were created in the early universe. And so the idea that it could somehow disrupt the fabric of space and time and you know, open portals to other dimensions seems odd to me, because the universe didn't at least do it readily in the early universe either. Maybe it does, and there's microscopic and we can't see it or something, but there aren't these gigantic dimensional rifts that we're aware of that have persisted since the beginning of time. And so doing this on the scale of the energies that we can get to make the quark-gluon plasmas seems a little bit strange to me. But, you know, serious people think about this, and, you know, there's always a way to do odd things. The creation of black holes is something that's, I think, interesting and definitely plausible. There's generally not concern about this because the speeds at which the black holes will be traveling at the moment that they're created far exceed the escape velocity of the Earth. So they would have just kind of popped right out and gone flying out into outer space. If you go to my blog, I've written a whole blog about this called A Thin Rain of Black Holes. So there's a whole post there. And the whole point in that blog is there was a lot of concern about the LHC doing this when we turned it on, making these mini black holes. But in fact, nature is doing this all the time. It is constantly bombarding us with cosmic rays from outer space that have the energy to make tiny black holes. And so nature's already doing it, whether we're trying to do it or not. And that's the whole point in that blog piece I wrote. So
could I have a brief moment here? I want to send an email. I mean, not email, a chat to everyone. Can you all see that?
Yep, I see it, Gloria.
This, you can copy that, just, you know, highlight it and then paste it somewhere. Because we'll have this talk up later today or tomorrow. And then I hope you will share it with your friends, because the only way people are going to hear about these talks, which you all agree are wonderful, is if you share them with your friends. And, you know, word of mouth is very slow. And I don't know how many people read our notices that come out, but active sharing with friends is a big help in a group like this. So I didn't mean to interrupt with the final question and answer, but I felt I better do this before everyone slips away on me. So please do copy it. That is the link to our whole website. This group has about a year's worth of talks on various topics there at the website, and introduce your friends, please. Okay.
Will do.
Thank you very much. This has been a very informative and interesting talk, and I'm not an astrophysicist, but I'm very much interested in the world around me. So thank you very, very much.
I'm glad you enjoyed it. Thank you.
Yeah, we're glad you could pop right on over to Chicago, Diane.
Come visit us in Sierra.
You know, we're talking about cold dark matter, and you have plenty of that up north this time of
At the
year.
moment, that is true. So
That's for sure.
I have one last question, if I may. Sorry, guys.
sure. Bruce has his hand up too. Do you have a question, Bruce, or no?
I just wanted to make a couple of comments. You mentioned Fred Hoyle earlier,
Yep.
and besides you know, his amazing scientific accomplishments and his crazy idea of the steady state universe, he wrote some great science fiction, a lot of which involved aliens traveling great distances and great speeds, and sometimes even sending their personalities via via radio waves to planet Earth.
Okay.
So he thought a lot about these questions, you know, 60, 70 years ago.
Okay. I didn't
And
know that. Yeah, that's great. Okay.
yeah, super cool stuff. And right now in the present day, we just hired a couple of new faculty members at the U of A in astronomy and planetary sciences from Sierra.
Oh, yes.
So,
Yeah.
so-
Kate and Sucrit, right?
yeah, amazing people. Sukrit is going to give a public lecture in about 2 weeks on planets and life and stuff like that.
Great.
And so they're going to be the first people that I email this link to. And then we will be inviting them to into future things. So that's all I wanted to say. And so back to Tim.
Thanks.
What's the, you mentioned a couple of times that we can travel without penalty into that. What do you mean by penalty? Is it physiological? Is it physics?
Yeah, so when I use that phrase, what I normally mean is without the effects of time dilation, right? The penalty for most of us is not being able to share the journey we made with our friends and family who stayed behind.
Oh,
So
I see.
when I use that phrase in the context of this talk, that's actually what I mean, right? No time dilation that you would experience because of the way we've constructed the travel.
Well, thanks for some very thought-provoking questions, Tim. And I see a long post from Bob in chat. Did you all, I don't know if you all read that, but he's got some real satirical ideas, sort of, I guess, about what would happen. So
yeah, there's lots of good stuff, right? And
I don't know, Bob, do you want to read your
covers it all, right?
Everybody got to see that.
Yeah. So
no, he's not reading. So.
Yeah, hi. So I was wondering whether you could send communication information through a wormhole. That would be easier than sending macroscopic objects.
yeah, so this is actually a really interesting and important question because, right, the wormhole itself, right, is a space-time tunnel, and so in some sense it's confined and it could in principle be hard to get through, right? So it has to open up and be large enough for your starship, whatever it is you want to send through. But in as much as it's an actual space-time pathway, normal communications via radio waves, you know, whatever you want, will propagate through the wormhole just as easily as they propagate through normal space, because they can't tell the difference. So you know, there's this kind of notion that maybe there are tiny microscopic wormholes that we can communicate through, but we would never be able to travel through. So maybe, you know, apparent superluminal communication through a wormhole network might be possible, whereas starship travel might not be. There of course are classic examples of kind of superluminal communication, but slow relativistic physical travel in science fiction. I think Ursula Le Guin is probably one of the earliest people to think about what's called an Ansible, typically, which is this kind of superluminal communication network. But that may entirely be possible, and certainly if the wormhole is traversable then by a ship, then it's also traversable by signals.
Okay, well, Bruce still has his hand up there. Or did you just not take your hand down, Bruce? No, Bruce is not answering, possibly maybe he just didn't take his hand down.
I didn't see it go down, so I think he forgot.
Yeah.
Okay.
So are there any others? Or if not, I put it up again. You see the 3 dots at the lower right of chat. You have 3 dots there. Using those 3 dots, click on them, and then the top option is save chat, and that will save it, I think, to your download place in your computer, wherever it saves downloads. So I recommend, if you want any of the things that are in chat, including the link to our YouTube group of our organization here, save chat, and it will go to your download. That's where it goes in my computer.
Yeah. Run that by me again.
When you're in these chat windows, first open chat, and if you
Okay.
can't see chat on your screen, go to more, and then one of the choices will be chat.
Yeah. Okay.
And
I'm in chat.
Then once you're in chat, you have 3 dots way at the lower, it's next to the little smile face icon, right at the lower right of chat. It says
Okay.
more when you hover over it. Click on it. The top option is save chat.
Yeah, I think I'm on my phone, so I don't have that option. But
Well,
maybe
it may be hidden. You may have it. You might want to do a user
Yeah.
question, because it may be there but hidden somewhere.
If you
can't
save the chat,
I'll
Gloria,
save it. I'll save it and I'll send it to you.
you're the best.
I think the
All right.
YouTube link was also in the announcement of the talk I saw. So it had the Zoom link and the YouTube link in the announcement.
Oh,
Oh,
great.
right. I don't know who reads the announcements.
I read
sometimes
it.
wonder-
That's how
I'm
I got
glad
the
you
Zoom
do,
link.
because it seems like we get a lot of the same people, and I'm thinking if everybody in that group was reading these. So I think actively getting the word out by sharing good talks, and I don't mean any talk, but good talks with your friends, that might help it to grow a little faster. So once again, we want to thank you very much, and we won't abuse your time. We will let you get on with the rest of your day. Big applause. from all
Well,
of
thank you,
us here.
everyone. It was a lot of fun. I
Yeah, we'd
enjoyed
love to have you come back and talk about some of those things Bob was bringing up, and that about, these other aspects that were not able to be covered today.
Yeah, I'm happy to do that. We can chat and find
Okay,
out.
that'll be great.
Okay.
All right, well, have a
All of
good
you have a great
Saturday.
weekend. Enjoy your
Thank
fall.
you.
And we'll do it again sometime.
We will.
Thank you.
Bye-bye.
Bye-bye.
Thank you, Gloria. This was amazing. Another amazing.
You're very
science
welcome.
Yes, thank you, Gloria, for arranging.
I'm a little dicey about next month. We have this woman in New Delhi, a woman professor in New Delhi, who's going to speak on women science fiction writers in India, but she hasn't been pinging me back. I've been trying to reach her. Just as a little insider talk. So it may have to end up being my presentation from TUSCON about the history of science fiction. I have a slideshow and live theater. So if she doesn't ping me back, we'll have to fill in with that. So hopefully
That would be
you won't
okay.
disappointed. Yeah,
That would be okay. Thank you.
you're very welcome. All right.
Okay.
Well, have a good day, everybody.
Okay.
I'll just
Thanks,
hang here till
thanks,
everybody's gone. All right. Bye-bye. I see Dr. Coster is still here, but he's not speaking even on chat. So, he disappeared now. I don't know if he can even interact with chat. It's a problem for him. I'm sorry about that. Ian, are you still there, or are you leaving?
I'm about to leave.
I hate to hang up on anybody, so
Don't worry about that.
anything else you want to say to me, or
And just thank you again for it. Very interesting and very capable speaker. And
Yeah, they're good.
it does raise questions as to how much we are allowed to lie in our science fiction, because we have to bend some rules, and we have to imagine some universes that aren't there in order to engage our reader.
That's
And,
true. Yeah, we can have numerous talks by numerous different people about that, because part of it is on a case-by-case basis. I don't know if there is a hard rule. You can go online, and there are some people who just give you a blanket answer, do this much, only what's needed for the plot, blah, blah, blah. But
yes, sure enough.
it's got to be case by case, because science
No,
fiction stories are so different. Oh, now Dr. Coster's coming back in. Poor
you're right.
guy.
It's
He has such terrible times. I feel really bad that, you know, he's having these connection problems, but then at
Yeah.
least now that we're putting it on YouTube, he can watch it after the fact.
Sure.
But I'd like him to be able to fully participate, but nothing I can do.
Now, what you give is good advice. It depends on the plot.
Yeah.
Only inject as much as you really have to get the plot to work, and don't introduce things that are trivial or unrelated to the plot. Every word must be linked back to the plot.
Right. You don't want to just dump a technical manual on anyone. That is, they used to do that. You could see that happening a long time ago. So, okay, well, I
Thank you,
don't
Gloria.
know,
Thanks a lot.
Dr. Coster, we're going to close down now, and I'm sorry if you're here because we can't seem to hear from you. But just go to the YouTube channel, which you know where it is, and we will have it up either today or tomorrow, and so people can begin sharing this talk. It was a very good one. So I'm going to say goodbye now, and we'll see you next month, hopefully with the woman who's coming or me.